All right, folks, I think we've made it. I think this is the last video. Thank you for staying on the journey with me. And actually, the last bit I want to talk about is pretty easy in my opinion. So sit back and relax, get your learn on, but it's not that complicated. I want to talk about one more method for approximately solving the traveling salesman problem. Remember, if you want to solve the traveling salesman problem and be sure that you got the best solution, you must use brute force, which is basically impossible even if you're using a computer. Take too many steps for a real world example, a large graph. If you're okay with not getting exactly the best possible answer, but maybe a pretty good answer, then you can use the sorted edges procedure. And there's one other common method that you can use, another approximate algorithm. It's called the nearest neighbor algorithm. All right, this is another approximate algorithm to solve the traveling salesman problem. Remember, if you want the best possible solution, you must use brute force, which is very time consuming. That's why instead in the real world people use approximate algorithms. The sorted edges is one, the nearest neighbor is another. Let's just try an example. It's quite easy to do. Let's do a small example, although you can do this on a big example with no problem. All right, here I have a weighted graph. This is the setup for the traveling salesman problem. And remember, we want to find a Hamilton circuit, that is, visits every vertex with the smallest total weight. All right. So here's how the nearest neighbor algorithm works. Its setup is different from the sorted edges in that you actually have a particular starting point when you do the nearest neighbor. So first of all, you choose some starting point. And this is, by choose, I mean typically this is given to you on if this was like a homework question, I would say use the nearest neighbor starting with D to find the cheap Hamilton circuit, whatever. Anyway, choose a starting point, and then you go from there to another vertex, and we pick the cheapest edge available. And then we continue that way, right? So you just go you start somewhere and you go step by step, and every time you pick the cheapest edge which is possible to pick. Now, you're not allowed to finish early, right? You can't make a circuit with yourself before you've hit all the vertices. So pick the cheapest edge, continue, and the rule is you only pick an edge to an unused vertex. All right, this is the rule. When you're doing this, you pick the cheapest edge, but you can only pick an edge which goes to a vertex that you didn't go to yet. All right, that's the whole procedure. Let's just try this example here. How about let's do this starting at A. And sorry, I have to erase some of these words. So I'll just call this the nearest neighbor starting at A. What does this give you? So I start at A, and you look at the picture, and you choose the cheapest edge from A. And I have three options, right? The 1, the 4, the 5. I choose the 1 because that's the cheapest. So next I go to B, A to B. And now from B, I have three choices here, the 1, the 1, the 2. I am not allowed to choose this one because it says only pick an edge to an unused vertex, but I started at A. So don't take the 1, take this one, B to C. So I'll go A, B, C. Then C, from C I have two choices, the 5 or the 3. Actually, I can't use the 5 because I've already used A, so I go to D. And actually, this is done now. I've visited all the vertices now, and so I put A just to finish off the circuit. This is the nearest neighbor algorithm. When you start at A, that's the circuit that you get. Just so we can compare things, what is actually the weight here of this Hamilton circuit that I just chose? I went A to B, that's 1. plus a B to C is 1, C to D is 3, D to A is 4. All right, so this total weight was 9. Okay, is that the best you can do on this graph? I don't know. 9 is pretty good. It's not so hard to do the brute force here, and you could check all possible Hamilton circuits. All right. What if instead I started somewhere else? How about if we start at D? What will happen if we start at D? Same graph, but I'm going to start at D. Starting at D. What do you say? If I start at D, my choices are the 2, the 4, the 3. I pick the 2 because that's the cheapest, so I go D to B. Then from B, my choices are the 1, or the 2. I can't choose the 2 because I already been to B. I could choose this one or this one. Now, here is slightly ambiguous. I didn't tell you what to do. What if there's a tie? I said just choose the cheapest edge every time. Let's just say if there's a tie, you can just pick whatever one you want. Choose at random. How about we go to the A? I don't know. All right. So from A, my choices are the 1, the 4, the 5. I can't do the 1 or the 4 because I've already been to B and D, so I must do the 5, which goes to C. And then from C, I have to go back to D because then I'll be done. All right. So this is the result if you do the nearest neighbor algorithm starting at D. And just so we can compare these answers, what is the weight this time? D to B is 2. B to A is 1. I'm supposed to be adding these. A to C is 5. And then C to D is 3. So this one, when I add them up, I get 10, right? 11. 11. Okay, so I guess this one was better than that one. You will see when you do the nearest neighbor algorithm, I just wanted to go through this to demonstrate. It does matter where you start. You will end up getting different answers. In this example, starting at A is better than starting at D. But it's hard to predict, like how do you know where the best place to start is? That's not clear at all. So you just have to pick a starting point. Or more likely on a homework or something, I will tell you what to use as the starting point. All right, let's try a bigger example. All right, here is a bigger example. I got 5 points here and a whole lot of edges. Let's see if we can do the nearest neighbor algorithm starting at whatever. I got to tell you where to start. Let's try. How about, can you try this? I think it's easy enough. You can just try. I'll say you try nearest neighbor starting at A, and again, do it again, twice, starting at, let's say, E this time. All right? See if you can do it. Did you do it? I hope you did it. If I start at A, you start here and you just choose your cheapest option every time. My choices will be 15, 27, 20, or 21, so I should take the 15 and go to E. Then from E, my choices are 12, 8, 13. I should take the 8, so that goes to C. From C, I got 32, 20, 8, 24. I already went to E, so I can't use the 8. I've already been to A, so I can't use the 20. So my choices, I guess I got to do the 24, so that would be D. And then from D, the only one left that I haven't used yet is B, so I got to go to B. And then from B to A, I got to finish off. All right, this is the one that you get when you start at A. What about starting at E? Okay, if I start at E, I gotta go E to C would be the 8, right? That's the best option from E. Now from C, I can go 32, 20, can't do the 8, or 24. I should do the 20. So E, C, A. Now from A, I got 15. Would be the cheapest, but I can't do that because I've already been to E. I can't do the 20. I better do the 21. So that's to B. And then from B, I got 21 I already did. 12 I can't do because that goes to E. 19 I could do, and 32 I can't do. So let's do the 19 to D, and then finish it off, go back to E. All right, this is the nearest neighbor circuit starting with E. I hope that worked out for you. As I've said before, the only way to guarantee that you get the best possible result from the traveling salesman problem is to do the brute force method. So I'm just going to say very specifically, the nearest neighbor algorithm does not always give the best solution. Does not always give the best solution. Right? The only way to guarantee the best possible solution is to do the brute force, which in the real world for a large graph is prohibitively complicated to do, even if you're using a computer. The nearest neighbor does not always give the best possible solution. In fact, there are some weird examples. Sometimes it gives actually a pretty bad solution. Sometimes it gives a bad one. Here's an example where it actually gives you the worst possible solution. So here is a graph with 4 vertices, and let's say the weights are like this: 1, 1, 2, 2, 1, and 1,000. All right. Now, any person looking at this, trying to just guess the best Hamilton circuit, will immediately say, all right, whatever you do, you better not use this one, A to D, because this one is obviously the worst and you can avoid this. But I'm here to show you, if you simply do the nearest neighbor algorithm, starting at A, actually this procedure will end up choosing the 1,000. See, you'll go A, and then your choices are 1, 2, or 1,000. So you take the 1, you go to B. From B, my choices are 1, 2, 1. I can't do this 1 again because that's where I just came. So I take the this 1 down to C. And then this C, my choices again are 1, 2, 1. I can't use that one, so I use this one and go to D. But now I have to return to A, and I can't go anywhere else. And so it's going to end up using that 1,000 weight edge, which of course is not the best way you could have done this, right? You could go this sort of X pattern. You use both of the 2's, which is a bummer, but you're not going to use the 1,000, which is much, much better. So this is actually definitely not the best solution. In fact, in this example, it's much, much worse than the best solution, which has just does this sort of 1, 2, 1, 2, like that. So that would be total weight 6 versus 1,003, which is, of course, much bigger. One thing that you can do to try and mitigate this fact, the fact is that the nearest neighbor algorithm sometimes does make bad choices. One thing you can do to minimize the bad choices that are made by the nearest neighbor algorithm is by varying the starting point. So we get different results, as we've seen already. We get different results by choosing different start points. Right? If I start here on an A, I'll go around there, and that's a very bad result. But if I started somewhere else, you can imagine you're going to get different, there are different possible results. We get different results by choosing different starting points. This actually leads us to a slight improvement on the nearest neighbor. It'll take you a little longer, but you'll get better results. We can simply check each different starting point. You might as well. These are so easy to do that you might as well just check each different starting point and then choose the best, right? There's a name for that. This is called the repeated nearest neighbor algorithm, or the repetitive nearest neighbor algorithm. It is kind of repetitive. You're doing the same thing over and over again, just using the different starting points. So this is called the repeated nearest neighbor algorithm. You simply choose every different starting point, work it out, and then figure out which one was the best out of all of those. Here's an example. Let's see if we can try. All right, first let's do this starting at A. So from A, I go 1, and then the 2, then the, I write it down, A to B first, all right? And then from B, I'm going to take the 2 down to D. Now from D, I can't go back to A or B. I got to go to C and then back to A. All right, so this is the nearest neighbor solution starting at A. What about if I started at B? We're just going to do each one of them. If I start at B, I should go over to A first. That's the 1. And then between the 4 and the 5, I should take the 4. That's D. And then from D, I can't do the 2. I better do the 6 to C, and then back to A. What if I started at C? Once you get the hang of these I hope you feel are very easy to do. At C, I should take the 3 first over to B. From B, I can go to the 1, which is to A. Then I got to do the 4, and then back to, so D and then C. All right, what if I started at D? This is the last one. I take the 2 up to B, and then the 1 over to A, and then I got to go down to C and back to D. All right, these are my 4 solutions, and then I'm going to pick the best one. Let's just choose the let's just compute the total weight of each one of these. This one, when I add them up, A to B is 1. I have to add these up. B to D is 2. D to C is 6. C to A is 5. So I add these up, that's 14. Okay? B, A, D, C, A. Well, I go B to A is 1. A to D is 4. D to C is 6. C to A is 5. That's 16, so this one was worse. C, B, A, D, C. C to B is 3. B to A is 1. A to D is 4. D to C is 6. Add them's up, I get 14 again. And D, B, A, C, D. This one, D to B is 2. B to A is 1. A to C is 5. C to D is 6. And when I add them up, I get 11, 14. Great. So I'm looking at trying to choose the best one. Apparently, the best one of these options is one of these 14s. Now, actually, you may notice this one right here, if you look carefully, and this one are the same Hamilton circuit. They are A, B, D, C, A. That would be, if I scribbled it, A to B to D to C to A. That's this one. And D to B to A to C to D, you will notice, is the same. D to B to A to C to D. Right? These are actually the reverse of each other, written with a different starting point, but they represent the same Hamilton circuit. This one, C, B, A, D, C. C, B, A, D, C. It's different, but it still gives you 14. So our best option, I'll say best in quotes, it may not actually be the best solution to the traveling salesman problem, but of these alternatives, our best option has weight 14, and it's, I mean, either one of these would be possible. I'll just write the first one, A, B, D, C, A. All right, this is the repeated nearest neighbor algorithm. It's a little better than just choosing one starting point and sticking with it. You might as well, if you've got a few extra minutes, you might as well choose all possible different starting points and then choose the best one that you get overall. I would like to try the repeated nearest neighbor algorithm on that other example that we did before with the 5 points. Let's see how it works out in that case with the 5 points. It's not much harder than this. Repetitive nearest neighbor algorithm. Remember this example? We already did 2 of these, right? We already did the one starting from A. We also did the one starting from E. Let's write down what are the others. There's one which starts with B, one from C, and one from D. All right, these are all straightforward to figure out. Let's do the B one. I think I should go to E first, then from E to C. Now from C, I think to A is the best I can do from there. And now I have to go to D and then back to B. All right, if I started at C, it would go the 8 first, so that's E. And then the 12 would be to B. And then from here, I think the 19 sends me to D. Then I have to go to A, then I have to go back to C. And then starting at D, I got the 13 will go to E. And then the 8 will go to C. And then from C, I think to A. Then I must go to B, because that's the one I haven't done, and then I go back to D to finish off the circuit. All right, these are the 5 different things that you obtain by doing the nearest neighbor on each of these starting points. And would you believe me if I said some of these actually are the same as the others? This one, D-E-C-A-B-D, is actually the same as this, E-C-A-B-D-E. They're just the same Hamilton circuit, but written with 2 different starting points, right? This one starts at D to E to C to A to B to D. This one, if I read it starting at D, it'll say D-E-C-A-B-D, which is the same as that. So actually these are the same. We don't have to check both of them. I want to check overall which one is the best, right? Are any of these others the same? I think actually this one and this one are the same, but reversed. This one goes B-D-A-C-E. And if you read this one backwards, it says B-D-A-C-E. So these also are the same. All right. So really I only have, and is this the same? B-D-C-E-A. Yeah, this is actually different from these other 2. So really all we need to check are the first 3 here, right? Because this is a copy of that one and this is a copy of that one. So I'm going to add up the weights to see of these 3 which is the best overall. Unfortunately, I got to erase my picture. I hope you have it written down. I have it written down on my paper. Let's add them up. So AECDBA would be, when I add these weights, the edge A to E is 15. The edge E to C is 8. The edge C to D is 24. Then I got D to B is 19. B to A is 21. All right. Add those numbers together, and I got 87. I think I did that right. Okay, check this one. E to C is 8. C to A is 20. A to B is 21. B to D is 19. D to E is 13. And when you add that up, you get, I got 81. I hope I did that right. And finally, BECADB, the B to E is 12. E to C is 8. C to A is 20. A to D is 27. And D to B is 19. I add those together. I get 40, 67, and 19. I get 86. And so, of all of these, which one is the best one that I found? It would be this one, E-C-A-B-D-E. So, E-C-A-B-D-E is the best using repeated nearest neighbor algorithm. All right. And folks, I think that's all I got for you. I hope that this end of the semester has gone all right for you. I've been trying my best. I hope that you have too. It's a shame it had to work out this way, but what else are you going to do? It's been a true unmitigated pleasure.